Okay, so the very last section, 6.13, is about improper integrals. So this is finally the end of chapter 6. By the end of this section, I hope that you are able to calculate an improper integral and make it proper enough to show the queen. So this is an example of an improper integral. All improper integrals mean is that somehow we're going out towards infinity. So we're accumulating area, but we're going all the way out to infinity. So it's improper because one limit of integration is infinite. So how do we deal with infinity in calculus class? We use limits. So this is another opportunity for us to get comfortable with limits. Instead of writing it as an integral from 1 to infinity, we're going to write it as an integral from 1 to b, and then we'll take the limit as b goes to infinity. And I recommend that you ignore the limit until you're all done with the integration process, and then you pay attention to the limit. So I'd recommend that you, like this part, just kind of set it aside and deal with the integral first. So as I'm dealing with this integral, I'm going to rewrite it with exponents. And it is not x to the negative 1, so we can use our power rule for exponents. We add 1, so we get negative 1, and we divide by negative 1, so we have negative x, and we have the integral we're going to evaluate from 1 to b. So now we plug in b, and we get negative 1 over b minus negative 1 over 1. Okay, we've now done all of the antiderivative and integration stuff that we can do. So now we're going to take the limit as b goes to infinity. And what I notice as b goes to infinity is that this section is going to go to 0 because we have negative 1 divided by infinity. So that's basically 0. And so our limit turns into 1, which means that all of this area, all the way out to infinity, starting at 1, all of that area is an area of 1. It kind of blows my mind because it feels like it should be infinity. It's even after doing calculus for more years than you've been alive, it feels like that area should not be finite. But it is if you follow this process of setting up a limit. You get a finite answer for that area. All right, this doesn't look very different, right? So this time we're going to go from 1 to infinity, but we're just going to do 1 over x and see what happens. You might notice by looking at the graph that 1 over x squared approaches the x-axis a lot faster than 1 over x does, or maybe a little bit faster, depending on how you look at it. So maybe this one also has an answer, but I would expect the answer to be bigger than 1. And maybe it doesn't have an answer. So our first step, we're going to rewrite it as a limit. So from 1 to b of 1 over x dx, and it's a limit as b goes to infinity. I'm going to ignore this part for a while. I'll come back to it. And so I'm going to do the antiderivative of 1 over x, which is natural log. Oops. And so that would be, well, I know b is positive because we're taking b out to infinity and we're starting at 1. So I don't need those absolute value bars. So natural log of b minus natural log of 1. And now we finished the integration, and so now we're going to do the limit as b goes to infinity. And when I do that, I have the natural log of b. And I don't know how comfortable you are with the natural log graph, but the natural log graph looks like this. And it does go as x goes to infinity, the natural log graph slowly goes to infinity. So the end behavior of that natural log graph as x goes to positive infinity is infinity, which means that this area is not 1, not a little bit bigger than 1. This area is infinite this area does do kind of what I expected on the last problem. This area goes on forever and it accumulates fast enough that it's infinity. What we say in calculus for an integral of this type where the area is infinite is we say that it diverges. There is no answer, diverger. There is no answer to this problem except that the integral diverges. You can't answer this question. So it's kind of crazy, like 1 over x squared converged to 1. 1 over x didn't even get close to 1. It went to infinity. So you can play a little bit, but it turns out, and you don't need to memorize this, if you have any exponent down here that's bigger than 1, then your integral is going to converge. And if you have an exponent that's smaller than 1, your integral will diverge. Definitely don't memorize that, but the reason is that if you have a smaller exponent, your graph is going to be farther away from the asymptote, and it turns out that it will be far enough away that the integral diverges. All right. Here's another one. We're going from 0 to negative infinity this time. And don't freak out if you're going to negative infinity. That just means that we're going to set up our limit as a goes to negative infinity, and we can totally do that, not a problem. And then we're going to go a to 0. And this looks to me like it's kind of calling out for a u substitution. So I'm going to make u equal to 3 minus x, and that would mean that du is equal to negative dx. So this is going to become, and I'm ignoring the limit for now, I'll come back to that. If I plug in 0 here, I get that this would be a 3. And if I plug in a, this would be a 3 minus a. And that's just using that u definition to figure out what those limits of integration are in terms of u. And so then I have u to the negative 1/2 du, and it's negative. And so then I'm going to do the antiderivative. So that would be negative u to the 1/2 divided by 1/2, so 2. And then we're going to go from 3 minus a to 3. And so this becomes negative 2 times the square root of 3 plus 2 times the square root of 3 minus a. And now it's time to come back to that limit. So now we're going to do the limit as a goes to negative infinity. I'm going to rewrite it because I was lazy and should have rewritten it before. So we have negative 2 root 3 plus 2 square root of 3 minus a. Well, if a is going to negative infinity, then 3 minus a is going to infinity, and the square root graph, the end behavior of the square root graph is that that graph goes to infinity, so this integral also diverges. All right, so some improper integrals are so improper that both of their limits of integration are improper. And before you can show these to the queen, you have to rewrite it as two separate limits. You can't be fancy and say the limit as a goes to infinity from negative a to a. It has to be two separate limits. The reason it has to be two separate limits is because if either one of those two limits diverges, then you don't have to go any further. And if even just a half of what you're dealing with diverges, then your improper integral will diverge. So you can choose any constant you want. Usually I go from 0. So I go from negative infinity to 0, splitting it up that way. And then from 0 to infinity. And because of additivity or the adjacent integral property, we can split it like this, and it's still equal to the integral from negative infinity to infinity. turn both of those into limits so that we can have a proper integral. This would be to negative infinity. I'm going to make that nicer. And this integration looks like it's a u substitution problem where we make u equal to negative x squared. So as we take that derivative, we get negative 2x dx. And so dx is equal to negative 1 over 2x du. So then I'm going to do that trick with my substitution where I'm going to change my limits of integration. So if I plug a into this definition for u, I get negative a squared. And if I plug 0 into that definition, I get 0. And so then I have negative 1/2 e to the u du. And I'll do the same thing with the other limit here. So this would be from 0 to negative b squared. And so then I'm still ignoring the limits, but I'll come back to those. So this would be negative 1/2 e to the u. Because the antiderivative is the same. And so this would be negative 1/2 e to the 0 is 1. And as a goes to negative infinity, e to a negative infinity squared. So this is going to be e raised to a really big but negative exponent. So this is going to go to 0. And so that side of the improper integral would be negative 1/2, and the other side would be positive 1/2, because this again, as b goes to positive infinity, this is going to go to 0. And so we have 1/2 and negative 1/2. So our integral is equal to 0. What that means is that we have the same amount of area below the x-axis as above the x-axis. And so the area will wind up canceling out in terms of that integral. There's a picture of it. Of course, I wrote right where the picture showed up, but that's a graph that shows why that would be 0. Here's an improper integral from -2 to infinity of the sine of x function. So if I rewrite this as the limit as b goes to infinity, you're going to take the antiderivative, which would be cosine of x, negative cosine of x. And if I do a limit as b goes to infinity of negative cosine of b, it doesn't really go to infinity, but cosine is doing that, the wobble thing. That's actually, it looks more like sine the way I graphed it, but you know what I mean. And it's not approaching any number as b goes to infinity. So this integral diverges because cosine doesn't have an end behavior that we can use to evaluate that improper integral. There is one more type of improper integral that I'll show you, and that is the type of improper integral that has a vertical asymptote.